All right, so we have the converse of all of these theorems. All those theorems we talked about yesterday. Remember, we had the alternate exterior, alternate interior, same side interior, same side exterior, all of those theorems. Today we are going to talk about the converse of the alternate, of all of these theorems. Remember, we had a couple days ago we had P implies Q, or if P then Q. The converse was just the opposite. We took Q and we said, hey, Q implies P. If Q, then P. It'd be like, if it's raining outside, then the ground is wet. All right. The converse of that would be if the ground is wet, then it's raining outside. So we're switching the hypothesis and the conclusion now. All right. So now the converse of the alternate exterior theorem says, hey, if we have two lines and transversal, all right, so here are the two lines, L and M. We don't know anything about L and M, all right, but we do know that they are cut by this transversal, all right? So the converse says, if those alternate interior angles are the same size, if angle 1 and angle 2 are the same measures, then line L is parallel to line M, all right? Maybe we have two lines like this, right? Maybe this is line L. Let me try that again. Maybe this is line, wow, all right, third time's a charm. There we go. There's line L, here's line M, all right? And then we're gonna cut a transversal. So let's look at the alternate exterior angles. So this might be angle 1 and this might be angle 2, right? Those are definitely alternate exterior. They are on the outside of the parallel lines and they are on alternate sides of the transversal. We don't know. Maybe these are both obtuse angles. So maybe this one is like 145 degrees. And maybe this one equals 130 degrees. All right. So if those alternate exterior angles are not congruent, then L and M are not parallel. All right, so basically all this says is if the alternate exterior angles are congruent, then we get L and M are parallel. All right. And then that's really going to be the whole idea of pretty much all the other ones. So the converse of the alternate interior angles. So again, if we have two lines, L and M, and they're cut by some transversal, if we get those alternate interior angles, so if we get angle 1 and angle 2, if those two angles end up being congruent, if they end up being the same size, then we know L is parallel to M. All right, keep in mind yesterday we said if we have two parallel lines, if it was given that these lines were parallel and it was cut by a transversal, it was given that angles 1 and angles 2 are congruent. Now we're saying the exact opposite. If we start out with angle 1 and angle 2 being congruent, then we get those two lines are parallel. So that is the converse of the alternate interior angle theorem. All right, then same side with corresponding. All right, so L and M are two lines. We have that transversal of angle 1 and angle 2. If those two corresponding angles are congruent, then we get L and M. Those are also parallel. All right, and keep in mind corresponding, that had to do more or less with like the location of where the angles are in reference to the parallel lines and the transversal. So angle 1 and angle 2, those are both above the parallel lines, but they are on the right side of the transversal. So since those are both on the top right of those two intersecting points, intersecting lines, those are the corresponding angles. All right, if 1 and 2 corresponding angles are congruent, then L and M are parallel. All right, now we had the two other theorems that talk about same side interior, same side exterior. Those were not congruent. Those were supplementary. All right, so if we have same side exterior angles, right, if we know angle 1 and angle 2, if we get that angle 1 and angle 2 equal 180 degrees, if angle 1 plus angle 2 is 180, they're supplementary, then we get angle L is, we get line L is parallel to line M. All right, so if I have two lines, here are my two lines. Here's my transversal. The same side interior. If I have a 75-degree angle right here and a 105-degree angle right here, well, 75 plus, oh, wait a minute. These are exterior. So I take that back. Maybe I have 75-degree angle here, a 105-degree angle here, right? Those are on the same side of the transversal. They are both on the outside of the intersecting lines. Remember, the outside is literally everything that's not in between the transversals. All right, so if I take those two numbers, so I take those two angles, 75 plus 105, and I add those together, and I get 180 degrees, then we can say these two lines, line L and line M, we say L is parallel to M. All right, maybe they're not. Maybe, you know, maybe this one up top is, I don't know, here, I'll just do another example down here. Maybe they look parallel. All right, so those look pretty parallel. All right, so if we try again, maybe this is a 160-degree angle. All right, maybe this is only 15 degrees. All right, if we add those up, 160 plus 15, that equals 175. Then these are not parallel. All right, because they don't add up to 180. So a lot of times you guys will look at these pictures and you'll say, oh, they look parallel, so they have to be parallel. No, that's not always the case. All right, so we have to go off of the information given to us. We can't just look at the picture and make these assumptions. We really have to be careful when we're doing all of that stuff. All right, and then same side interior, same kind of thing. If angle 1 and angle 2, if those are same side interior angles, if they add up to 180 degrees, if they are supplementary, then we have two parallel lines. Now, there are three theorems that I want to talk about today, three like new ones, I guess. And these seem pretty obvious, I guess, but there was a homework problem yesterday or last night that you made an assumption that we hadn't really covered yet. And I think this theorem 2-8 or 2.8 is going to clear that up. So if two lines are parallel to the same line, they are parallel to each other. All right, so what that means is we know so just looking at this picture here, we know that line A is parallel to line C. All right, we know that by the arrows on the picture. All right, the arrows on the picture also tell us that line B is parallel to line C. Theorem 2.8, it seems kind of obvious, but theorem 2.8 says if we have this idea, right, so if we can kind of go backwards and we can snake through this, if A is parallel to C and C is parallel to B, well then we get for free that A is parallel to C. So that's kind of an important idea, but we need to be careful about that. We definitely need to state that explicitly. And I want to go back to that homework from yesterday. So this one right here, number 3. Can you guys see this on my screen? Can you see my PDF that's open? Yeah. Okay, so this L and M, and then M and N are parallel. And then it says prove angle 1 is equal to angle 12. All right, so a lot of people, what they wanted to do is they wanted to just go straight for the kill and say angle 1 is congruent to angle 12 by alternate exterior angles. All right, now we can't say that. Say that again?
We're only seeing the theorem 2-8 page.
Oh, all right, hang on. Let's do this. Can you see this picture?
Yes.
Okay. Sorry. Whenever I go to another screen, I guess it doesn't show you that. All right, so this was a homework problem from last night. A lot of people wanted, right, you had your statements and your reasons. A lot of people just wanted to say angle 1 is congruent to angle 12 by alternate exterior angles, right? They just wanted to skip straight to that. But we couldn't do that yet because looking at this picture, we only know that those two lines are parallel and these two lines are parallel. All right. What we needed to do is we needed to establish another step. We needed to say, before that, we needed to say line L is parallel to line N. All right. And we hadn't talked about that theorem yet, but last night's homework, you could have said this. You could have said theorem 2-8 or something. I'm not going to make you remember what numbers they are. I don't know what that is. 2-8. I have no idea what that is. So if you didn't want to say theorem 2-8, totally fine. You could just say the transitive property, right? Because that's literally what it is, right? L is parallel to M and N is parallel to M. Therefore, this must be true. That's the transitive property. So once you establish that these lines are parallel, then yeah, you can say angle 1 is congruent to angle 12 because these two lines are parallel and they're cut by this transversal. So angle 1 is congruent to angle 12 because those are alternate exterior angles. So we just have to be careful on something like that. Somebody said, did I mean B? Did I make a mistake somewhere?
Yeah, it's just in the last one. It's you pass it. It's fine.
Yep, totally made a mistake. Dang it. All right, that should have been a B, right? Is that what you're talking about?
Yeah.
Yep.
Thanks.
All right, my bad. Sorry about that. All right, so maybe I'll just re-record this because I'm making a lot of mistakes now. All right, so theorem 2.9 or 2-9. Theorem 2.9, kind of the same thing, except instead of parallel, it's perpendicular. So if if two lines are perpendicular to the same line, all right, so we have a symbol for perpendicular we haven't covered yet. If two lines are perpendicular, so that means they intersect at a 90-degree angle, then that means they're parallel to each other. So in this picture here, we know that A, here's that new symbol, upside down capital T. If A is perpendicular to C, all right, and B is perpendicular to C, all right, then A is parallel to B. All right, and that's like a special case of the corresponding angles, right? These two right angles, those are corresponding angles. They are in the upper left side of those intersections. They are congruent, therefore A and B have to be parallel. That's really all that one's saying. I don't know why it's a special theorem, I guess because it's perpendicular, but that's really all that one's saying. Now this next one, this is kind of like an obscure theorem, but we got to talk about it anyways. So if we have some line, all right, any line, all right, we're going to call this line L. All right, I want to type this out because this gets kind of wordy. So if there is a point, I guess P, if there's a point P somewhere off of line L, then there is exactly one line that passes through P that is parallel to L. All right, so that's pretty wordy. So let's talk about what that says. So if I have some point P, right? So I got line L. Here's my point P, right here. It can be anywhere. It doesn't matter where. Directly above, directly below. It really doesn't matter. All right. There's some point off of line L. What that means is it's literally not sitting on line L. Then there's exactly one line that passes through point P that is parallel to L. All right. So that line, if I draw that line, that is perfectly parallel with L. That is the only line I can draw through P that is exactly parallel with L. If I try to draw another one, right, that's not parallel. If I try to draw another one, that's obviously not parallel because they're going to intersect somewhere down here. These intersect somewhere over there, right? So that's kind of a weird theorem, but it's kind of an important idea. And then also we could say the same thing, except parallel, we could say perpendicular if we wanted to. Right? So this theorem holds true for parallel lines and perpendicular lines. So if you have some point P anywhere off of line L, you can only draw one line through point P that is parallel to L. It's really all that one's saying. All right, that was the homework problem we did earlier. And I think, all right, so let's see here. Let's look at an example. We are building a gate. All right, so Bailey's making a gate. How does Bailey know the vertical boards V and W are parallel? All right, so if you want to think about this one, here's the boards. Right, we can change the boards into lines. Line A is our transversal. So how do we know V and W are parallel? Any suggestions, any ideas?
Because they're perpendicular.
Yeah, exactly, right? Look at line A and line V. Those are perpendicular, and then line A and line W are also perpendicular. Right? These two lines, these two vertical lines, are both perpendicular to the same line. Thus, V and W are parallel. All right. Now, what should the measure of angle 1 be to ensure board B is parallel to board A? So here is, we can change these boards into lines. We have our transversal cut down. We know this angle right here is 35. All right, so what they are concerned about, it's kind of hard to see in the picture. They want to know what should angle 1 be, this angle right here. And then I'll do that in another color. So this angle right here. So we know this angle down here is a 35. So if we want those lines to be parallel, what do those two angles need to add up to be?
180.
They need to add up to be 180. So you're just going to do 35 plus whatever that angle needs to be. Whenever we don't know a value, we usually throw a variable in for it. And we're just going to call it, 35 plus x equals 180. If you subtract 35 from both sides, we're going to say, oh, well, x, or I guess we could call it angle 1, just needs to be, what is that, 145? It needs to be 145 degrees. So we can just sticker 145 right there. So that was the converse of the same side interior angles. If these two angles add up to be 180, if these two angles are supplementary, then lines or boards A and B are parallel. Oh man, oh shoot, how many more do I have? Bailey also needs to cut board to parallel. What should measure of angle 2 be? All right, so we established at angle 1. So we have these two, we had our transversal. We know that angle 1, we said that had to have been 145. This was 35, right? What should angle 2 be? Angle 2, if we draw that board, angle 2, so that is looking at lines C and lines V. All right, they want it to be parallel with board A. So keep in mind, board A has a 90-degree angle right here. All right, so angle 2 also needs to be 90 degrees. So angle 2 must equal 90 degrees. They both need to be perpendicular to the same line, or those same side interior angles need to add up to 180. All right, so we have our statements, and we have our, I'm going to make those smaller. We have our statements, and we have our reasons. All right, step 1, always write down your givens. That's the easiest way to get 1 out of 5 points on these proofs, is to write down your givens. All right, step 2. We know angle 1 is congruent to angle 2. We are trying to show that L and M are parallel. This is the converse of the alternate interior angles theorem. All right, so we cannot use the definition of alternate interior angles to prove its own theorem. But there's another one we could use, maybe the corresponding angles theorem, right? That one looks pretty good. We have an angle 3 there, so we might as well use it. We could say, well, if you notice, if you look at this picture, angle 1 and angle 3, those are congruent, all right? And we know that. We know angle 1 and 3 are congruent because they're vertical angles. Remember, vertical angles happen whenever you have some sort of like crisscross, some kind of X. The ones that are opposite are congruent. So angle 1 has to be congruent to angle 2 in that picture down at the bottom I just drew. All right. So now what we can say is angle 2 is congruent to angle 3. All right, so angle 2 is congruent to angle 3. That was our transitive property, right? We said 2 and 1 are equal, 1 and 3 are equal. Therefore, 2 and 3 must be equal. All right, so that was our transitive property. So now I think we have it. We can say L is parallel to M. And how do we know that? Well, we know that by the converse of the corresponding angles theorem. We know that 2 and 3 are corresponding angles, and since they are congruent, L and M are parallel. So this would be the converse of corresponding angles theorem. All right, and there we have it. All right, so we just proved the converse of the alternate interior angles theorem. We proved this theorem without using any definitions of alternate interior angles. All right, so now, just like we did yesterday, we could have used all of those theorems when we're proving stuff. Now I'm going to let you guys use all of the theorems we talked about today when we're doing proofs. So what I mean by that is you have all of these converse theorems at your disposal, and then also you have these 3 theorems at your disposal if you want to use those as well, right? So each day we're gonna start, I guess, unlocking more and more theorems for you guys to use when you are doing your proofs.